Hello everyone, welcome back. So hopefully now my voice won't be quite so crazy as it was the first hour. John was kind enough to give me some water, and so now hopefully I'll be able to talk with even more enthusiasm about all of these wonderful topics. So as you recall from the first hour, we were talking about how using smaller sensors requires us to make some sacrifices. So we either have to use shorter lenses in order to get the same field of view or to capture the same amount in a particular image, or we have to be able to increase the sensitivity, for example, of a particular sensor in order to get as much brightness, so to speak, or as much signal out of that particular size. And so just to hammer this point home, and actually and as a teaser, there's going to be a part of this lecture that's probably going to completely blow your mind, where we will hopefully dispel a myth of compact cameras versus digital SLRs. I want to again show you this particular to-scale image of the different sized sensors. However, there's a difference. So these are exactly the same. These are the same size sensors that we saw before, but the difference this time is in the resolution of the two sensors. So in this case now, we have the sensor on the left is only 0.5 megapixels versus the sensor on the right, which is 6 megapixels. And if you do the math, you realize that the one on the left, so while the one on the right still continues to have 3,000 pixels across, 2,000 pixels down, the one on the left now has much fewer. It has about 875 pixels across by about 571 pixels down. But the reason that this is important is that now the pixels, each pixel is the exact same size between the two sensors. So now we really have cropped out the center part of this large sensor. We took the middle portion of it and we put it over here, and that is exactly what we have. We have the same size pixels, so now we get a sort of different result from what happened previously, where we talked about two differently sized sensors that had the same number of megapixels. So let's again go through our thought experiments where we had one lens and we put that lens in front of each sensor. So we put that lens in front of the sensor on the right. We get again a picture of the entire room, for example. Now let's say that we put that same lens on the sensor to the left. And what happens now? What do we see in our image? Yep, so it's just the center, but everything else being equal, it's going to look exactly the same. It's just going to be as if we have cropped out the center 0.5 megapixels from the original image, or from the image of the larger sensor. Now, you may say, well, okay, this seems sort of silly. Why on earth would we do this? Well, keep in mind, again, that the pixels are now the exact same size. So now what we have is that each pixel on the left receives just as much light as each pixel on the right, and this means that we can get just as much quality out of both, but at the expense of what? The resolution. So whereas now we're able to keep the same amount of signal that we had originally, we lose the resolution, we lose the field of view, we lose a good number of things that were available on the sensor at the right. Okay, so conversely, imagine that we revert back to this smaller sensor that has the higher number of megapixels, the 6 megapixels. We talked about how each pixel now actually has to deal with less amount of light. So because they're actually smaller, they get fewer photons that reach each pixel. So if we were to continue designing a camera that is going to be representatively smaller on the left side than the one on the right. So let's say that we just designed a camera on the right side where we could take an image of the entire room, and then now we want to design a camera where we can take an image of the entire room for a sensor on the left. So this means that we have to make the focal length shorter in order to get more of the image in, and this actually has an impact on more than just the width of the image. And so just to give you an idea of what we are going to be talking about, what are some of the features or some of the impacts of using a compact digital camera versus a larger one. And I'm talking about how the image itself might look. So when we're talking about a compact digital camera versus a digital SLR, in your mind and sort of typically what would you expect would be the difference between the two if we took an image? So at the same settings, so they're exposed the same, they have the same field of view. Do the images differ at all? Really, nobody has any ideas how they would look different. Okay, so let's say that we set both to an f number of 2.8. So those of you that are familiar with compact digital cameras, what maybe you have looked at larger format cameras with maybe a sense of awe or wonderment about the images. So what makes those SLR images look different? Depth of field, okay, good, yeah. So typically, we expect compact cameras to have a much larger depth of field for the same f number. So if we make everything else the same, we use the same ISO, same shutter speed, the same f number, but we have two cameras side by side, where really the only difference now is that they're two separate, well, okay, that's a big difference, but if they're two separate cameras, but they're of the same scene, they're exposed exactly the same, you would expect the smaller camera to have a much larger depth of field. But I have to say that this is something of a myth. To think that digital SLRs cannot have the same depth of field is actually a myth that's been propagated probably because of how we think of f numbers. So when we think of f numbers, we know that it's a ratio of what? I know I'm making you guys work today. You're like, come on, it's Monday, but yes. What's the f number? Ratio of? Yeah, focal length and diameter. Okay, good. So now when we're dealing with the same f number across different cameras, we might sometimes see a difference of something like this, where one camera has very wide or very large depth of field, and the other camera does not. But what does, if you remember that this f number actually is a ratio of this focal length and this diameter, you'll realize that some things have changed. First of all, in this smaller sensor, in order to get the same field of view, so in order to capture the same width of this particular ruler, we have to use a much shorter focal length. So that means if we're using a shorter focal length and we have the same f number between the two cameras, something else has changed as well. And what is that? Not the ISO, I'm talking about the lens itself. Yeah, the diameter of the lens. So the actual aperture, the size of the aperture has shrunk as well. So not only has the lens become smaller because the focal length is smaller, but the aperture has shrunk as well. Now, this image shows that there is not actually a significant difference between compact camera and a digital SLR in terms of the depth of field that is possible. Now, this tells you something very, very important, and that is that digital SLRs of the same year, basically of the same amount of technology as their counterpart compact cameras, are capable of not only very short depth of field so that you can get nice blurry, creamy backgrounds, they're also capable of the same thing that compact digital cameras are as well. So when you take a photo with a compact digital camera, you have a sort of range of f numbers that you're allowed to use. Keep in mind that that is only a subset of what digital SLRs are capable of doing. And that is what this image is trying to show us. Now, if we try to go over this, and there's actually on the website, there's a link to an article written by a guy named Roger Clark, and he goes into excruciating detail about why this is, and I guarantee you will have to read this article several times in order to understand it. But I will try to describe why this happens. So let's say that we have two cameras. We have a digital SLR and we have a compact camera. And so just for the sake of argument, and to try to keep as many things as similar as possible, they'll be from the same manufacturer, in this case Canon. They'll be from the same era of technology, so they were released at about the same time, which means that really the differences between them are the size of the sensor and the size of the lens. Of course, there's differences in the electronics themselves and the features, but we're not worried about that stuff. We're actually worried about the optics itself, or the optical path as the light enters into the camera. So here, at the very bottom and very top images, realize that these are three separate images, and I know they're sort of stacked almost confusingly on top of each other. On the top most and bottom most images, we have a Canon 1D, which is it's not quite full frame, but it's just ever so slightly smaller than a full frame sensor. And we're using a lens that is 28 millimeters at an aperture of about f3.5. Okay, now on the Canon camera, we are using a much smaller sensor, and in order to get the same field of view, remember we have to shorten the lens itself, and so we are using, rather than a 28 millimeter lens, we're using an 8 millimeter lens, and we get the same amount within the image, the same amount of the scene. Now it's important also to note that these two also have approximately the same amount of megapixels. So they're both about 8 megapixels, I think. So that means that the pixels on this image, or on this camera, are much, much, much smaller than the ones in the larger Canon SLR. Okay, so we take an image. So we try to keep things relatively the same. We take an image at about ISO 50 here, and about ISO, well, let's see. Oh, okay, so if we take an image at ISO 640, which is a lot larger, then we get a certain shutter speed. But you see that keeping the F number the same at 3.5, it looks as though this image in the middle, the compact digital camera, has much larger depth of field. But what's important here is not the number, the F number ratio, it is the size of the aperture itself. So if we calculate how much smaller the aperture is in this one, because keep in mind that the lens, the focal length is shorter, so that means the aperture had to shrink as well, we find out that this aperture is about, I think, 2.2 times smaller than the aperture that is here. And that's, I'm just talking about the diameter itself. And that happens to be also the difference in the size of the sensors as well. So this Canon camera here is about 2.2 times smaller in terms of the crop factor. So if we make up for this difference, if we try to figure out exactly how much smaller or how much less light this smaller aperture is letting in, we do some calculations and we realize that what was 3.5 over here is now f13 up top. Okay, so this means that now between these two cameras, we have the exact same size aperture. We have different sized lenses, but that's because we have to try to get the same field of view, or the same amount of information within both. But now that we have stopped down this, lens to have a smaller aperture, what do we have to do to try to get still a reasonably fast shutter speed? Increase something. Yep, so if we increase the ISO, then we will be able to recoup that shutter speed. And in fact, if you were to carefully study the two images, you would be able to determine that these two images have just about the same amount of noise. Even though we increased the ISO, you notice that we went from 50 to 640. So let's see, okay. So we can do this math. 50 divide root this. Okay, so let's see. So what we got when we made, oh come on, when we stopped down the aperture by a certain amount, we got a certain amount less light that was entering into the camera. However, it's the same number of photons now that are hitting both sensors. Because it's the same size aperture, this means that the same number of photons are entering into both cameras at the same time, which means that if we increase the ISO, we get about the same noise, about the same amount of noise that we did in the smaller sensor. So we get then, in the end, the ability to mimic a much smaller sensor just by using not only a higher ISO, but also a smaller aperture, because now we're making all of these things approximately equal, approximately the same. So this is understandably kind of confusing. But again, just to reiterate this, what's important to realize is that compact digital cameras, even though they traditionally have been thought to have a much larger depth of field, it's really only because everything is smaller. And with that smallness comes also this decrease in size of the aperture itself, which means a couple of things happen. We get a longer depth of field, but also we get fewer photons that enter. So this smaller sensor is at a disadvantage because it has, just by nature, with the same F number, fewer photons entering into the lens. And this would make perfect sense if you looked at the size difference between each of these lenses. You have a big SLR lens, it's going to let in a lot of light, and you have a small compact camera lens, and it's not going to let in as much light. So in order to battle this, the camera manufacturers have to essentially increase the sensitivity of these smaller sensors to try to get everything else to be the same. So in order to get the same, in order to use the same F number and the same shutter speed and the same ISO, this means they have to boost the sensitivity, which makes them noisier. So for the same amount of technology, the size really does matter. The bigger you go, the more light you will have, the better the quality you will have. But of course, this comes at the expense of size, weight, expense in terms of the cost of the system and all of its little doodads and stuff that you have to buy for it. So it is, of course, a trade-off. And again, the compact camera is just a subset of what is possible with the larger SLR cameras. Now, we've been talking about pixel size and about how when we change the size of the sensor and try to keep the megapixels the same, or the quantity of pixels on that sensor the same size, we get a decrease in maybe the amount of signal or in the amount of light that we're able to hold. And we can imagine this. If we go back to our analogy of the buckets, let's say that we have a sensor, an SLR size sensor that has it has 6 megapixels, it has very large buckets, and we have something that looks like this, where we can fill up those buckets with these 4 photons. Well, not fill it up, but we fill it up to about this amount. So what's happening is that we get a certain amount of light that enters into the camera and onto the sensor, and we're able to record so much of that. Now, if we have a much smaller bucket, as what would happen with a small sensor digital camera, it doesn't take as long to fill up that bucket, because this bucket is now narrower, it's not as wide. It may be the same depth, even though there's no real analogy in terms of that. But if we think about this sort of abstractly in terms of the width, if the same amount of light falls onto it, so if we have these 4 photons that falls onto it, it increases faster. But remember that these smaller compact cameras that have these smaller pixels usually also have the smaller apertures. They have the smaller lenses, which means the apertures themselves are smaller, which means that less light is coming in. So maybe we're going to get half as much light, for example. We typically get a lot less than that, but just as an example, we only get 2 photons in instead. And so now we see that it is about approximately the same level of brightness. And so even though it doesn't take as many photons, it's noisier. It's harder for us to measure from something that's not, from a bucket that's not as large. If we have a very, very large bucket, it's easier for us to try to measure the amount of water that's fallen into it. But if we have a very narrow, very small bucket, it's not going to be as easy for us to measure. So we're going to get significantly more amounts of noise from this sensor on the right. And so what is important here is it's something called the signal to noise ratio. So it's the amount of signal that we get compared to the amount of noise that it takes for us to try to read that particular signal. Now, if you are looking for a digital camera, I don't necessarily recommend that you do this, but something that's very interesting from an academic standpoint is something called DxOMark. So this is a company where they go into excruciating quantitative detail about sensors themselves, and they try to capture a lot of information about the sensors that exist within digital cameras. And one of the things, so I'll just pick a, let's see, this Nikon, for example, and they measure a number of things about these particular sensors as soon as it comes up, including the dynamic range, how sensitive they are to light, how good their performance is in terms of color and in terms of ISO sensitivity. And one of the things that you'll notice that's very interesting about a lot of digital cameras, so I'm just showing you this not really to advertise any of these cameras, but just to show you some of the information that we can get from these sensors. You'll notice that if this gray line is sort of the optimal amount of sensitivity in terms of, let's say ISO 100, it's actually going to be as sensitive as a film level ISO 100. Just about every camera is not quite as sensitive as film is itself. So we see this on just about every digital camera. This is a way that they're able to cheat. And one of the things that we also see is a signal to noise ratio at various ISO levels. And you'll see that there's a downward slope here, and I'll describe that probably not today, but in probably the next lecture. This is something that's very, very important to us, and the dynamic range as well. So we can see that this particular camera, which is an expensive Nikon camera, does have just about 12 stops of dynamic range. Now, if you let me go back to this image here, remember that I said that dynamic range is basically the division of the biggest signal, or the most amount of photons that it is able to capture, or the full bucket, divided by the smallest signal that we can reasonably capture. So if we have two cameras, one that has a very wide bucket like this and can fill up on a lot of these photons, versus a much smaller bucket that will fill up twice as quickly, we can see that we have much larger dynamic range out of this bucket just because it is a much larger bucket. We are able to get a bigger signal out of it. And this is very important as it relates to ISO and to dynamic range. Now, just to show you a few more things from this website, and again, I think it's interesting to look at, but I'm not sure you should necessarily base purchase decisions off of this, because it's getting into a level of detail that just doesn't really matter, I think. I think a lot of modern digital cameras have very, very good sensors, but this is useful, I think, as a tool to understand how these cameras work and what is going on behind the scenes. So tonal range, as you remember, what's the difference between dynamic range and tonal range? I'm sorry?
Dynamic range has to do with the amount of light stops, but tonal range has to do with color.
Close, yes. So whereas dynamic range deals with the range of light, so the maximum and minimum amount of light that we're able to cover, tonal range, it's not quite colors, but it's the amount of subtle gradations within that range. So if we have a very low tonal range, for example, from this very deep black to this very high white, then we'll sort of see a stepping stone of gray as it gets slightly lighter, slightly lighter, slightly lighter. But if we have a very large tonal range within this dynamic range, then we see a lot of the grays in between. So we just see this smooth gray change from this deep black to this bright white. So having both a dynamic range and a tonal range to match is important, because if you have a very wide tonal range, it's not going to mean very much if when you see a color of a nice sky, for example, it looks like there's a big blue splotch and then a slightly lighter blue splotch. That's just not going to cut it for us as photographers. So both of these is important, but of course color sensitivity as well. So this is something that's actually just marked differently, and it's how sensitive a sensor might be to various amounts of color. And as we'll see, this actually can be impacted by the sensor itself. And of course the signal to noise ratio, so how much signal we're actually getting based on the amount of noise. And so there's a lot of religious debates on the internet, and if you do research for digital cameras, you might narrow it down based on features alone or based on price for a variety of your own factors that you have in mind. You might narrow it down to 2, 3, maybe 4 cameras, and then you'll probably start Googling for these cameras to see what's going to come up, see whether people like them, dislike them, and most people will probably come up with similar conclusions as you did and realize that there's a couple of cameras that are kind of in the same range, and most people will compare them. And a lot of times you get into these religious debates about megapixels and sensor sizes. And yes, this is very important, but it's also important to realize that it's more than just the pixel size itself that impacts the image quality. Now, in absolute terms, let's say that we get to a certain technological point where we just simply cannot advance in technology anymore. We just cannot get any better at designing sensors or at being able to eliminate noise in sensors or a variety of other things. Now, that is when this sensor size or this pixel size is really absolutely going to matter. Another time this is going to matter is when you're looking at 2 cameras that were released at about the same time. And at the same level of technology, larger pixels will almost always be better than smaller pixels. But the way things are progressing, we kind of get into the point where we can make pixels slightly smaller and be able to get some good quality out of them. Now, in absolute terms, of course, the size of the pixels does matter. And for the longest time, I always went into a very long rant in E7 about how, oh, the megapixel war, it's really, really stupid. You should not pay any attention to megapixels. And to a certain degree, that's true today as well. But luckily, camera manufacturers are now seeing the light as well in the same sort of thing. And in fact, Canon recently announced a compact camera within a certain line of compact cameras, and I forget exactly the model number. But in the newest model, they actually decreased the number of megapixels in that camera, with the sole reason of getting larger pixels out of it and therefore getting better dynamic range, better low light performance out of that camera. And as we slowly reach the point of where we just cannot physically get any better data out of photons than what we have, and by the way, we are sort of reaching that point where sensors can detect, a couple of photons. Like it's very impressive what these sensors are able to do. As we approach that point, then megapixels will matter in terms of smaller will be better, because then you will have a larger pixel well, you'll be able to capture more light, you'll be able to get better quality. But there is something to be said about newer cameras that have maybe just slightly larger amounts of megapixels. And yes, I don't want you to get the wrong idea that more megapixels is better. That's not what I'm saying here at all. I just don't want you to get caught up again in these religious debates between, oh, it absolutely has to have fewer megapixels to have the absolute best quality possible. Sometimes there's other factors where they can get around that. They can have slightly better megapixels and be able to retain the same quality or maybe even increase the quality at the same time as well. And as you will see in the next lecture, there's a couple of pretty obvious ways that they will be able to do this.